All right. So my name is Evgeniy. I'm from Intel Compilers and Languages Group. And today I'm going to talk about how one can implement an OpenCL compiler for CPU using LLVM. Here's the disclaimer I have to show you. And our objective today is to use this very short 20 minutes in order to discover different kinds of collaborations that we may have within the OpenCL part of LLVM community. We have quite good collaboration within the front end, but my action to you is to kind of extend that and go beyond front end into the middle end and the back end. At first, let's recap how we can map OpenCL concepts onto CPU. Although OpenCL offers both types, both task and data parallelism, we're going to focus today only on data parallelism. An OpenCL developer writes a kernel that addresses only one point within the problem space, that is a work item. Several work items are organized into work groups, and the combination of work groups comprise the whole problem space called the range. OpenCL execution model allows us the following mapping onto the CPU. At first, we're going to take a work item, wrap it into the loop. Then we're going to combine several work items and place them together on a CMD register. Then these vector iterations will be executed using a software thread. And those software threads will be executed concurrently on a multi-core machine. Let's dig deeper into the compiler stack. Here I'll try to highlight what main differences OpenCL brings in to the standard LLVM compilation flow. At first, we're going to take the lib clang. We're going to wrap it up in a new entity library that we call lib-OpenCL clang. And we're also going to incorporate Kronos SPIR-V LLVM byweight translator in order to accept SPIR-V input mandated by the OpenCL 2.1 specification. Then we're going to inject a bunch of OpenCL specific passes into the LLVM pass manager. Quite late in the optimization stage, we're going to link in the OpenCL built-in implementation library. And since OpenCL mandates us to provide just-in-time compilation model, we're going to use MCJIT as a just-in-time compiler engine. Let's take a closer look at the front end. The main challenge within the OpenCL is to have different kinds of inputs and at the same time target a variety of devices. As far as the CPU is concerned, with x86 precompiled binary path is the simplest one. Since everything is precompiled, we just take that, we bypass the whole compilation flow, and we just send it straight to the execution. With SPIR-1.2, the situation is a little bit more complicated, as SPIR-1.2 by its specification is in form of LLVM 3.2, which does not exactly match the OpenCL version that is used to implement the device middleends and backends. So here we introduce a new entity called LLVM quote-unquote equalizer. That takes care of the LLVM differences. So what it does is fixes up not only the LLVM version issues, but also handling differences and different representations of OpenCL built-ins such as pipe, enqueue, and other stuff. In order to consume SPIR-V input, we incorporate Kronos SPIR-V LLVM byweight translator that emits LLVM that is pretty close to trunk, but does not exactly follow it. So what we do is that we run it through this LLVM equalizer again. And with regards to classic online compilation, we just take libclang, wrap it in this libopencl clang library, and we're going to use SPIR in order to produce LLVM IR that's version that's strong. So what this lib OpenCL clang is? Well, essentially, it is a wrapper for the libclang. Its main feature is to provide in-memory compilation from the source. It also features precompiled headers for OpenCL build-ins in order to speed up the compilation of OpenCL kernels. And it also offers C-style APIs for different actions mandated by the OpenCL specification, like compile, link, get kernel arc-info, and the different stuff. And it also provides quite a stable API that does not expose any of the LLVM internals to be stable for different device middlelands to use. Let's take a look at one of the examples. Here I show you the compile method signature. It takes a program source, which is a C string. It takes input headers that we can pass there. It also takes precompiled header buffer that contains precompiled headers. We also pass different compile options that OpenCL developer provides, and we pass an OpenCL version there. Here is an example of a link method. It just takes the input binaries and it links them together with the options provided by the user. This library is open sourced, so everyone is welcome to take a look. Now let's move on to the middle end. The main challenge in the middle end is to optimize a heterogeneous language that OpenCL C is. Many features of OpenCL come from GPU and FPGA world, like whether it's going to be a barrier, non-flat memory model with different kinds of address spaces, spatial data struct called images, and pipes. Let's take a close look how we can resolve barrier in OpenCL. Just to remind you all, barrier is an OpenCL built-in function that all work items within the work group must hit before any of them continue their execution. And simply put, this barrier splits the control flow along the barrier calls and creates go-to and switch-driven state machine in order to enforce the barrier semantics. Let's take a look at a simple example. So we have two pieces of the code split by the barrier, and we're going to apply the following transformation. We're going to have to introduce two new counters, one for the current work item and one for the current barrier. Then we're going to use this switch-driven go-to state machine in order to loop first within the code 1 and then loop within the code 2. Let's make an example a little bit more complicated. Let's introduce a value of x that depends on the work item ID, and let's make this value cross the barrier. And if we follow the same approach without putting in too much thinking into it, and since the value of x depend on work item ID, we're going to see that the value of x is going to be different for every work item, and we actually can spot a flaw here. The value of x will gonna be the same for all the work items, which renders this transformation incorrect. The first thing that comes to mind is that we can store all the value of x's for all the work items into a special buffer. Then we're going to replace all the usages of this value using lobes and stores. Let's take a look at the example on the right-hand side. We're going to realize that both x and y depend on our work item ID here. We're going to use the scope analysis in order to realize that only x crosses the barrier. And we're going to mark only x. We're going to record its size, and we're going to record the offset of all the x values in this special buffer. And we're also going to record the next value of x within the x subset of this special buffer. So to put it more formally, what we are going to do is give every barrier instruction a unique number. We're going to calculate all the predecessors for each of the barrier instructions. And with regard to LLVM IR values, we're going to take a look on those values that depend on the work item ID. We're going to analyze the scope of those values and mark only those values that cross the barrier calls. We're going to calculate the total size of those values and record the appropriate offsets. With regards to the transformation phase, we need to introduce two new counters, with one for current work item ID and the other for the current barrier. And for every value, we're going to store it into the special buffer. And load this value in the places where it is present within the scope of the barrier, and replace all the usages of this value with this new loaded value. And every barrier instruction will be replaced by this switch-driven go-to-state machine, followed by the appropriate memory fence. So in this example, we have only one barrier. We're going to give it the number 1. And the barrier is number 0 will always be the prologue of the kernel. So the predecessor of the barrier 1 is barrier number 0. Let's take a look at this example. Now, let's call a function foo that has a barrier inside it. What we're going to do then? If we follow the approach that I have just described, we're going to require several jumps into and outside of the function, which is not the path we would like to follow. So the obvious answer is to why not inline it, but that is not always possible. So what are we going to do is place new and artificial barriers around the function call and into the calling function. We're going to add a dummy barrier at the beginning of this function and a real barrier at the end. And we're going to surround the call to such function with a barrier and the dummy barrier at the end. And what the dummy barrier is it only counts towards the calculation of the barrier predecessors, and it does not have the real barrier semantics. So my call to you is to exchange the feedback, ask questions, and extend the collaboration within the OpenCL community beyond the front end. Well, thank you. Do you have any questions?
So if you have any questions, you can feel free to use one of the microphones or contact me and I will bring this over to you.
Thank you for your great talks. And I have a question about barriers, that why you don't use conditional variables. I mean, why you use a state machine instead of existing solution?
Well, there was a thought floating in the air about it, but we really haven't put into much thinking into it yet. So that's a great suggestion. Thank you, and we're gonna definitely take a look into this.
Because the reason is that you seems to be like using a busy loops to model a barrier which is not always true, like in terms of performance or something. So
Oh.
because like conditional variable use some kind of sleep.
Okay. Okay.
Yeah. And
All right. Yeah. I got you. Yes.
Yeah. And the last question is that can you go more details about the OpenCL specific passes you mentioned in the second slides, or?
What we have there is basically stuff to address all of those non-CPU friendly things that OpenCL has, like the address space resolution, I don't know, different kind of image transformation with different kinds of samplers that OpenCL has. So what else we have there? The built-in linker to link in the implementation of OpenCL functions. Also a vector function kernel OpenCL vectorizer is also there. Probably these are all the things, pretty much.
Okay, thank you.
All right.
Is it on?
Yes.
Can you hear me?
Yes.
So what kind of cooperations are you looking at? Is it more like extending LLVM passes or like even changing LLVM passes?
Well, my thought was that there are several CPU vendors out there, right? And I think they're going to have the same issues as that we have, right? So probably that collaboration should move into that direction.
Okay, but you're suggesting to improve the passes. So because now currently we do things in Clang.
Yeah.
But I understand that if you don't develop for AMD GPU or PTX, then you basically very limited what you can do in LLVM. So
Yeah.
just to understand, you actually want to improve LLVM passes or maybe add passes.
Yes.
Okay.
Yes.
So what would it make sense for you to reuse x86 backend, or like, because if you are improving passes, then often you need to demonstrate, like provide a test or something. So what kind of backend do you think you could target for that?
You mean with OpenCL?
Yeah.
Well, the first backend that comes into mind is x86. Yeah.
So would it make sense to add like environment OpenCL into x86 triple or something like that?
Yeah, that's a good thing, probably. Something like kind of x86, something OpenCL, right? Like AMD GPU, right? Probably that's one of these to go, yes.
I will suggest to start LLVM dev thread on that.
Yeah,
Sounds
of course.
interesting.
That's yes, that's the next step. Thank you.
How does this compare to POCL? Do you know?
Sorry, to what?
POCL, P-O-C-L.
All right, so this is a OpenCL implementation that is highly optimized for Intel hardware. So probably that's the main difference to the POCL, POCL, right?
Okay. At Xilinx, we also needed this kind of stuff. We wanted to support OpenCL on FPGA. And we did a different strategy where instead of having a state machine, we actually create loops. Like, so what you do with a state machine is a loop, the work item loops.
Yeah.
But it's not a clean loop. It's a state machine, so it's hard to analyze for the rest of LLVM. Yeah. And we prefer to create basically a for loop, and we actually the same analysis work basically to create an actual for loop, but we had to add new barriers from time to time.
Yeah.
And in the end, it performed quite well. So I don't know if this is better or which one is better.
Yeah, we can take it offline.
Yeah.
Yeah, surely. Thanks.
So if that's it, thank you, Eugene, for the talk. And you may talk to him later, or do what you will. But thank you.
Yeah, thanks.